Hey there, Seahawks. It's Miss Adams, and in this video, we're going to talk about sampling distributions and the central limit theorem. All right, so why do samples look different? So we're going to look at an example with some dice. So let the random variable x represent the sum of the rolls of two fair dice. We take a random sample of 5 rolls and find the sample mean. All right, so we roll the dice 5 times. We add the 2 dice together because it's the sum of the 2 dice. All right, so the first time I rolled, I added them together, I got a 7, then I got a 4, then I got a 9, then I got a 3, then I got a 12. So those are my 5 sums from rolling the 2 dice 5 times. All right, and then x bar, the sample mean, would be 7. I added them all up and I divided by 5. All right, so I did this again. I did another 5 rolls of 2 dice, added them together, found their sums, averaged them, found the sample mean. And again, all right, so rolling 2 dice produces 11 unique sums, all right, and there's 36 total sums, like all the possibilities, right? We don't know what results we get from any individual roll. The dice are independent, all right, so when I'm rolling the dice, those are independent events. We could determine all possible means for 5 rolls. The sample means vary, and some sample means are more likely than others, right? So some of the sums, I can make that combination more than others. Okay. All right, another example with proportions. So in a close election, a candidate has the support of 51% of the voters. Of course, no one knows this until after the election. 5 pollsters each take a random sample of 1,000 voters to determine whether the candidate will win. So I have 5 separate pollsters. They randomly sample 1,000 voters. Okay, these pollsters are probably not sampling the same 1,000 people. Maybe there's an overlap, but probably not, right? These are probably like different areas, whatever. So each pollster is getting 1,000 voters and calculating the proportion of voters that would vote for this candidate, all right? So this is a sampling distribution. I'm taking a sample, I'm calculating a statistic, and then I'm repeating that process over and over and over again, all right? So my first sample proportion, p hat, is 0.55 or 55%. My next sample proportion is 0.48, then I have 0.52, I have 0.47, and 0.49. Okay, so those are my sample proportions, okay? And if I did this many, many, many times, I would start to see some trends, right? Here is the true population proportion, which we know after the election was over, was 51%. Right? So a sampling distribution of a statistic is the distribution of values for the statistic of all possible samples of the same size from a given population. All right, so let's say we have a population of all U.S. teenagers. We are interested in the average resting heart rate of teenagers. We use a sample size of n equals 50, which means we are taking a random sample of 50 U.S. teens. Determine the sample mean resting heart rate from that sample. So I take a sample of 50 U.S. teens, I get their heart rate, and then I find the average of all of those heart rates. Then do this process again and again and again until you have collected the sample mean for all possible samples. All right, it's difficult to get the sample mean from all possible samples, right? So like I'd have to have this person in each arrangement. It would be a lot. So we use the central limit theorem, or CLT, which we'll talk about a little bit later. The distribution of sample proportions. The population has a fixed proportion. We call that P. To find the population proportion, a sample is taken and a sample proportion, P hat, is calculated. Sorry, I had a wrong word there. If samples are repeatedly taken with the same sample size, all right, then the mean of the sampling distribution would be the same as the population proportion. All All right, so mu of p hat would be equal to p if we know p. The standard deviation would be the square root of p times 1 minus p over n. All right, conditions to check for this assumption. So it has to meet these 3 conditions so that I can use a normal model and then I can go further into other things. So it has to be randomization. So the data needs to come from a random sample or a randomized experiment. The 10% condition checks for independence. If I'm sampling without replacement, then my sample size has to be less than 1/10 of the population size. And then large counts condition, I have to have at least 10 successes and at least 10 failures. This is also like our normal condition. This is the one. N times p has to be greater than or equal to 10. That'd be at least 10 successes. N times 1 minus p has to be greater than or equal to 10. That'd be at least 10 failures. If all conditions have been met, then we use a normal model of sample proportions. So our normal model would have a mean p and a standard deviation square root of p times 1 minus p over n. All right, according to the manufacturer of the candy Skittles, 20% of the candy produced is the color red. What is the probability that given a large bag of Skittles with 58 candies, that we get at least 17 red? Okay, so 20% coming from the company, they said 20% are red. So that is our population proportion. 58 candies are in the bag, so that's my sample size, so that's n. And then I want to see if I can get more than 17. So 17 out of 58 is almost 30%. All right, so it's 0.293. So if it's supposed to be 20%, what's the probability that I get closer to 30%? That's what I'm checking. All right, so in order to be able to use a normal CDF to figure this out, I have to check that the conditions for normality are met. All right, so random, they didn't say anything about random, so usually you're looking for it. It's usually going to be stated. But I'm going to assume that the Skittle packages are filled randomly, right? That there's a random mix of all the different colors in there. The 10% condition, 58, which is the sample size, is less than 1/10 of all Skittles. And my normal condition when I'm working with proportions is n times p has to be greater than or equal to 10. So 58 times probability of success 0.2 is 11.6, which is greater than or equal to 10. And 58 times 0.8 is 46.4, which is greater than or equal to 10. All right, so I would want to make sure I put this greater than or equal to 10, check, greater than or equal to 10, check. All right. So all conditions are met. I need to now find the mean and the standard deviation. So mu of p hat is going to be equal to p, which is 0.2. The standard deviation of p hat is going to be the square root of p times 1 minus p over n. P is the population proportion, which is 0.2. 1 minus p will be 1 minus 0.2, which gives me 0.8, over n, which is 58. That gives me 0.0525. So now I can use a normal distribution. I have the mean and the standard deviation. So I'm going to draw my normal curve. I'm going to go ahead and put my center here at 0.2. And I want to find the probability of getting a proportion greater than 0.293. So I'm going to go to 0.293. I'm finding the probability that's more than, or at least, so greater than or equal to that amount. So I'm going to do a normal CDF. My lower bound is going to be 0.293. My upper bound is going to be 9999. My mean is going to be 0.2. My standard deviation is going to be 0.053. And I get 0.0397, or almost 4%. So there's about a 4% chance of getting about 30% red when it should be 20% red. All right, distribution of sample means. So when I'm working with means, things are going to be a little bit different than when I'm working with proportions. So the population has a fixed mean. We call that mu. To find the population mean, a sample mean is taken, or a sample is taken and the sample mean is calculated. So x bar is our sample mean. If samples are repeatedly taken with the same sample size, then the mean of the sampling distribution would be the same as the population mean. So mu of x bar would be equal to mu, and the standard deviation would be the standard deviation, population standard deviation divided by the square root of n. Okay. So I'm going to check the conditions to see if I can use a normal distribution to kind of solve problems. The conditions here are it still needs to come from a random sample or a random experiment. The 10% condition, which again is checking for independence. If I'm sampling without replacement, then n has to be less than or equal to 1/10 of the population size. Sometimes it'll just tell you that it's independent, that'll be stated. And then the normal condition, when I'm working with means, there's 3 ways that this could be met. The parent population is normal, which they'll usually tell you, or is very safe to assume. The sample size is large, so n is greater than or equal to 30. That would be using the central limit theorem. Or the sample shows no strong skew or outlier. So this would be, if those other 2 are not met, then I have to kind of make a histogram or a normal probability plot to check this. All right, so we said that would be using the central limit theorem, so we need to know what is the central limit theorem, all right? So there are 2 assumptions. The sampled values must be independent, and the sample size n must be large enough. All right, so this is kind of the 2 pieces, the last 2 pieces of those conditions. The mean of a random sample has a sampling distribution whose samples can be approximated by a normal distribution. The larger the sample, the better the normal approximation will be. Generally speaking, n has to be greater than or equal to 30 for us to go ahead with that. And this is regardless of the shape of the population distribution. So even if the population distribution is very strongly skewed, the central limit theorem, if our sample size is large enough, and I'm doing a sampling distribution, then my sampling distribution will be approximately normal if I'm taking large enough samples. Okay. An automaker does quality control tests on the paint thickness of different points on its car parts since there is some variability in the painting process. A certain part has a target thickness of 2 millimeters. The distribution of thickness on this part is skewed to the right with a mean of 2 millimeters and a standard deviation of 0.5 millimeters. A quality control check on this part involves taking a random sample of 100 points and calculating the mean thickness of those points, assuming the stated mean and standard deviation of the thickness are correct. What is the probability that the mean thickness in the sample of 100 points is within 0.1 millimeters of the target value? Okay, so this is a sampling distribution. I can't just jump right into a normal CDF because I have a set number of, like, my sample size. So I'm taking sampling distributions. I'm taking a sample of 100, calculating the mean, repeating that process. All right, so I need to find the mean of the sampling distribution and the standard deviation of the sampling distribution. So the mean is going to be equal to the mean of 2 millimeters. The standard deviation is going to be the population standard deviation divided by the square root of 100. All right, so it'd be 0.05 millimeters. Now I need to check my conditions to make sure I can use a normal distribution for this. So random, it was stated that they took a random sample of 100 points. The 10% condition, 100 is less than 1/10 of all points that I could take on that part. And normal, 100 is my sample size, which is greater than or equal to 30. So the central limit theorem applies there, and my conditions are met, so a normal model is appropriate. So I'm going to draw my normal curve. I have a mean of 2 and a standard deviation of 0.05. Again, make sure you're using the standard deviation from a sampling distribution, not the original standard deviation that they told you for the parent data. So my mean is 2. They said I want to find the probability that x is between or within 0.1 millimeters. So I'm going to go back 0.1 and forward 0.1, so that's between 1.9 and 2.1. All right, so again, my standard deviation is 0.05, so that would be 2 standard deviations above and below. And we know that the 68, 95, 99.7, it's going to be about 95%. But I'm going to go ahead and do a normal CDF. My lower bound would be 1.9. my upper bound would be 2.1, my mean would be 2, and my standard deviation 0.05, and I get 0.954, which is pretty close to what we would have expected using the empirical rule. All right, if I'm doing a sampling distribution for a difference in samples, so a difference in proportions or difference in means, then I'm going to be using my reference sheet. All right, so for 2 proportions or for 2 means, I'm going to be using the reference sheet to figure out what the mean and the standard deviation are, and then I'm going to follow the steps just as I did with the other ones, except for you have to find the mean and the standard deviation with 2 pieces first. All right, go Seahawks.